Hi, folks. This is Shaun Walsh. I'm the CMO at Peak Nano, and I am probably the only person on this conversation that does not have a PhD, so I am not going to be talking about technology. However, I do want to talk about one of the core things, which is commercialization. And at this point in time, I think to say that the world needs fusion energy is an understatement. I don't care which prognosticator you talk to, we are now living in the age of electricity. And some of the easy benchmarks to look at here are it used to be about 3/10 of a watt to do a search on Google. Now it's 3 watts. Multiply that times tens of billions of inquiries every day, and you start to see where the AI story comes in. If you believe our friends at JP Morgan, we'll be spending somewhere on the order of $5 trillion on AI infrastructure. A great deal of that is going to be power generation as well. A number of the hyperscalers are deeply invested in all the members of this webcast. And we know that about $2 trillion is going to be spent on new utilities. So all of this boils down to one fundamental thing. The world needs more power, and they need it very cost effectively. And I think that's one of the other things that fusion energy brings to the table in a 24/7 dispatchable way that renewables don't today. So if we look at what's driving that, the obvious growth in power grid. And again, I'm not going to read everything that's on this slide, but if you look at what's happening inside power grids today, solid state transformers, solid state high frequency switching, and AI management are changing the way in which power grids operate, and that requires a different approach to energy, and fusion will be able to help deliver that. AI data centers continue to grow, and fusion energy is one of the solutions they're looking for in the future. Then we obviously have the different types of fusion energy that need their own energy to get started, the first queue, so to speak. And then EVs and charging, as we have seen with many of the world events right now, demand for that class of storage continue, or that class of transportation continues to grow. So, what does all that mean as we look forward? Uh, this is a report that Mike and the folks from Ignition Research have done. And if you look at the forecast today and you say fusion gets to about 20% of power generation over the next 30, 40 years to 2050, that means we need somewhere between 1,500 and 2,000 plants at 1 gigawatt each in order to make this work. And that growth curve is one of the biggest challenges for both the supply chain and the power infrastructure that would support that supply chain and these new fusion systems. So, as we look at some of the next speakers in this section, we'll start to see where that comes into play. And most importantly, how can we drive the right price point? And a while back, Bob Mumgard published a blog that talked about major milestones for fusion. And one of the statements that stuck with me was fusion power must reach $50 per megawatt hour to be a price point that's competitive to win in the market. And I think that really is a good target for the industry. So here's a chart that came from Lazard. It was also published in Bloomberg. And if you look at the other sources of power that are out there, if fusion hits any starting at 50 and even $100 per megawatt, it's going to be amongst the most cost-effective types of fusion there is. So that's the end of my prepared remarks. I'm going to hand it over to Carolyn and let her tell you how she's going to help make that cost target happen in the world.
Thanks, Shaun. I appreciate it. All right, before we jump into E&P Technologies, I'd like to kind of take a step back and recognize the evolution of many fusion approaches that Shaun mentioned that we have today. All of these approaches we see, they vary in scientific reasoning, but as the industry starts to settle in, you're starting to see similar or repeat approach models emerge. And one that has a lot of backing and is picking up trend is impedance matched inertial confinement. So IMG architecture is really what I would consider a breakthrough innovation on the path to commercialization. From my perspective, it unlocks what I would consider an underestimated power within its design. And I'm not strictly talking about the actual performance power from the system. I'm talking about the power of simple and scalable operations that it holds. So many key advantages from this IMG approach include streamlined designs, which means less hardware, which typically means less complications, but it also has module built systems that enhance its manufacturing and maintenance activities. So this shift from traditional single shot research machines that you tend to see in typical pulsed power solutions to scalable modular power systems drives an entirely new challenge that we see today, which is demanding that we have repeatable, reliable hardware at scale. And that's precisely where E&P Technologies comes in. So, my name is Caroline Sorrick. I'm the co-founder and CEO of E&P Technologies, where at our core, we design and manufacture advanced high voltage capacitors for extreme energy environments, just like fusion, other pulse power applications, and advanced power systems that can be found in defense and aerospace as well. So the company was founded to challenge what has historically been a very stagnant, overseas dominated field out of a direct firsthand experience working in the fusion system development industry. We recognized there was a major gap in the supply chain for high performance pulse power components. And we also saw that capacitor technology wasn't evolving at the pace required for these next generation systems. So our focus started to shift on rethinking how these components are not only designed, built, but how they're operated. So we do this through a series of cutting edge initiatives that we'll cover in upcoming slides today. So at E&P Technologies, again, we're not focused on just delivering hardware. In fact, we are working to innovate solutions that can meet the demands of these extreme applications. So our products evolve alongside our customer needs, keeping pace with cutting edge requirements of industries just like fusion. We're not just developing existing components, we're re-envisioning what capacitors can actually do, and we're pushing the boundaries of durability, performance, and reliability in these extreme environments by partnering with innovators like Peak Nano. So at E&P, innovation, it really is more than just a buzzword of or developmental concept. It's about how we transform the way we design, test, and manufacture capacitors. So we're doing this through a series of initiatives that really advance our products by building an AI-driven design platform to help speed up iteration, but also to integrate our customers' requirements from the start. This will allow us to build an all-inclusive solution based on final operating conditions and even suggest solutions down to the micro level, such as high-performance material mixtures like peak nanofilms. This will allow us to deliver more compact and the most high-performing products as possible. In fact, our products can also feature advanced embedded diagnostics and feedback technology that will be paired with an advanced AI software for real-time insights such as performance highlights, predictive maintenance alerts, and even troubleshooting support and suggestions. So this will allow you to know exactly how your capacitor is performing or trending to perform in your system. And on the manufacturing side, the way we're leaning into innovation is we're using advanced automation and predictable with repeatable processing to ensure that we're reshaping and reaching scaled production. We're also pairing this with a pod-based method to enable higher throughput and mass batching. To simply summarize as a whole, we're rethinking every step along the way to deliver faster, smarter, and more reliable solutions. But you might be asking, why does all this innovation matter? And I'll tell you specifically why it matters to fusion. Capacitors are mission critical to the majority of the fusion approaches that we're seeing today, particularly the one we mentioned earlier, such as inertial confinement, IMG. And we're talking about systems that are storing megajoules of energy and discharging within nanoseconds of precision. And we're doing that repeatably, reliably, and at massive scales. In fact, fusion at power plant levels, to me, isn't just a one-time scientific demonstration challenge. It's actually an operating challenge, which means components like capacitors must function seamlessly on an ongoing, stress-filled basis, and manufacturing must also scale to meet those demands. And this is the exact problem that E&P exists to solve today. So, lastly, I want to highlight three meaningful elements of how we evolve with the companies that we work with. Some of these are our cultural tenets, such as E&P. Speed is not just a goal for us, it's how we truly lean into our operating conditions and our culture. We take innovation seriously and we move fast by combining novel technologies up front into our baseline products rather than waiting for the industry to catch up. Next, we prioritize use cases. So every solution is analyzed and designed around demanding power requirements from first conversation to final output of the product, which then leads us to delivering actual hardware. We believe truly in the art of building early and the power of the prototype, which will allow us to iterate from real world data and validation through testing campaigns, not just through endless design concept cycles or even software modeling. So there is truly no better way to optimize a solution than to allow the hardware to communicate its needs to you directly. So with that, thanks for allowing us to share a little bit about what we're building here at E&P. I'm now going to hand it off to Mason to explain how our partnership with Peak Nano enhances our products.
Thanks, Caroline. Very exciting to hear about all of your approach towards an advanced capacitor solution. So one of the things that got us excited about working with E&P Tech was the fact that capacitors are kind of a stale technology right now. For basically the last 50 years, you've had companies basically using polypropylene as their base material. And I think what excites us about working with E&P Tech is the fact that you have that innovative background and looking to kind of push the boundaries of what a capacitor is and how a capacitor performs. And we do likewise at the film level. So my name is Mason Wolak. I'm the VP of Capacitor Development here at Peak Nano. I'm going to walk you through our approaches to enable a material system that we can get out to cap manufacturers that gives advanced performance in very challenging applications such as fusion. So the basis of everything that we do is nanolayering. So what we do is we take two different polymers, we melt them together, and then we stack and fold them into a multi-layer structure. So what this allows is for us to target different polymers with different dielectric, mechanical, and thermal properties, and then put those two materials into a layer structure with a very precise definition of the composition of the two materials and the number of layers. And that unlocks a new property set in capacitor film that is unlike any property set of a off-the-shelf type of material. Peak Nano has two commercial solutions towards fusion, and these are NanoPlex HDC film, which is our high dielectric constant film. This film is getting traction in the IMG type of pulse power systems for inertial fusion. This material is designed specifically to have very high dielectric constant, which means that you can store more energy in the same unit of volume, which is very critical when it comes to building these IMG pulse power modules, because the smaller that you can make the capacitor, the more capacitors you can fit per module, which means you can shrink down the total size of the module and decrease the cost of construction for the module, right? Because there's a lot of cabling because you're delivering megajoules of energy. So you need very expensive thick cabling. So decreasing the size of the module offsets the cost of construction. Our other material is NanoPlex LDF, and this material is designed specifically for high temperature operation and to mimic the dielectric characteristics of polypropylene, which is a material that most cap manufacturers are used to using with and designing with. So what we've done is we've taken the operational temperature of polypropylene and extended it out to about 135 degrees C to unlock higher performance in capacitors that require polypropylene-like performance as a baseline. So I'm going to start a little bit with the HDC film. As I mentioned before, we have two commercial offerings. our 3125 and our 4125. The dielectric constant of these two materials are 3.7 and 4.8 respectively. So you're more than double the dielectric constant of polypropylene. The advantage of the high dielectric constant coupled with the very high breakdown strength of our material is that you can store more energy per unit volume. So there are always trade-offs in designing the layer structure between the dielectric constant you can achieve and the dissipation factor that you get for the material. So this gives us a full design space that we can work in. So the nice thing about the two commercial offerings within HDC is that the source materials are exactly the same. But as we change the internal layer structure, we change the bulk property of the film. Next slide, please. To give you an idea of how powerful this is, this slide basically shows more than 10 different formulations that we've developed with HDC. So on the right-hand side, you see some internal layer structures that are imaged with scanning electron microscopy. So you can see that the top and the bottom layer structure here have completely different compositions. The one on the top has very thick layers of our high dielectric constant material, which is the white layers. And the one on the bottom has very thin layers of that high dielectric constant material. And that allows us to move the dielectric constant and the charge storage capability of the capacitor film around as a function of the composition. And from a fabrication standpoint, the only difficulty here is we just kind of change some knobs in terms of running our melt, and that changes the composition. So we do this inline. We don't have to take our system down, do any cleanouts or anything like that. We can run this in real time and change from one composition to the other and generate completely different property sets of the capacitor film that we're making. So as we work with fusion companies, we start to understand what the rep rates of their capacitors and their IMG system is designed towards. That allows us to then match, well, how much dissipation factor can you tolerate? If you're at a low rep rate and you can tolerate high dissipation factor, we can deliver a solution with a very, very high dielectric constant that would have 3 to 4 or 5 times the energy density of standard polypropylene capacitors. But if you need a trade-off between rep rate and energy density, we can go in and design a material that's specific for your system. Thank you. I'm going to switch gears here for a second and talk about NanoPlex LDF's film. This is designed for essentially a completely different type of application space, but it will definitely have use in fusion systems. For example, if in magnetic fusion where you're operating at higher frequency, you're generating a lot more heat in your capacitor. So your capacitor film needs to stand up to that heat without failure. So the LDF formulation is essentially polypropylene with thin layers of a thermal stabilizing polymer. And what these thin layers of polymer that are thermal stabilizing do is build out dimensional stability in the polypropylene. So the major aging mechanism for polypropylene is shrinkage over time. So as polypropylene is exposed to high temperature and high voltage, it will actually shrink and degrade in performance. So our approach here is to thermally stabilize the polypropylene such that it does not shrink at high voltage and high temperature. And if you look at this video here, Jalen, can you kick this off? You'll actually see the polypropylene winding shrinks, whereas the LDF winding does not. So this is a stop motion video, 150 degrees C for 1.5 hours. So what this does is unlock the ability to use NanoPlex LDF and high frequency fusion applications to extend out device lifetime and cut system maintenance costs. Next slide, please. So we're working with a variety of different capacitor manufacturers to develop this material into commercial solutions specifically for fusion. And we've been able to characterize the film as outperforming polypropylene in terms of high breakdown strength at high temperature, decreased loss, and more stable dissipation out to 160 degrees C, and an improvement in the stability of the capacitance as a function of temperature. So in the graphics shown here, the LDF data is in green, and you can see a distinct advantage over polypropylene in all three of these application or operational use cases. So these are two materials that we've been developing at Peak. We have multiple new materials that are under development. So we're targeting high energy density, high temperature performance, and the ability to shrink down the footprint of the capacitors that are made with our film. And the partnerships that we have with companies like E&P allow us to drive our high performance film into a high performance capacitor that's designed specifically for fusion applications. So I'm going to bring all of this around full circle here and leave you with the slide that Shaun started with, talking about the technology demands that are really driving the need for high performance capacitors. And although fusion is a huge portion of this, there's obviously other applications outside of fusion that require this level of high performance capacitor. Thanks.